Hi everyone, in this video we'll be looking at the properties of acids. At the end of this video, you should be able to state the physical and chemical properties of acids, as well as to write chemical equations and ionic equations to represent their reactions. We will also be looking at the tests for gases, hydrogen and carbon dioxide, which are produced from acid reactions. This topic is very interesting because it is quite immediately relatable to your everyday life, and I'm sure you will have some prior knowledge of what acids are already. We all know that acids are corrosive. So the video you're watching here is concentrated sulfuric acid added to an orange. You saw what the acid did to an orange, right? So why is it we still find acids very commonly in our everyday life? Specifically, right, you can find them quite a lot in your skincare products. Well, it all boils down to the type of acid that you are using. Okay, so there are acids that are so-called strong acids, there are acids that are so-called weak acids. It also boils down to the concentration of the acid that you use. So for example, the acids that we use in the school lab tend to be more diluted compared to what is used commercially or for research purposes. When I was in my teens, I remember I suffered quite a bad acne kind of breakout. And one of the skincare products that I used was one that contains salicylic acid. Maybe you might be interested to go and find out on your own. Why is it acne treatment products tend to contain certain kinds of acids, and how do they actually work? As scientific knowledge advanced over the years, the concept of the acid has also changed. So in the past, right, in the 1600s, people used to classify acids as things that taste sour, corrosive liquids, they just call them acids. Not too long later, the definition of acids was changed to substances that turn the litmus indicator red. In the 1800s, this definition was yet again changed to acids being substances that contain hydrogen. What you all learn now in secondary school is the definition of acid as a substance that dissolves in water to produce hydrogen ions. Okay, so this definition that we learn in the textbook now is the one taken from the 1800s. Well, you might ask, has the definition of acids changed since then? So the answer is actually yes. Okay, so if you go on to learn further chemistry, you will learn other definitions of acids which are broader and include more substances, the Bronsted-Lowry theory of acids, as well as the Lewis theory of acids. Okay, so they are different definitions of acids that have a different scope. So we start with the definition in your notes with an acid being a substance that dissociates or ionizes in water to produce hydrogen ions. The term dissociates means to break apart. So for example, hydrochloric acid is HCl. And you know that from what we learned in chemical bonding that the H and Cl are joined by a covalent bond. Dissociate means that this covalent bond breaks. Okay, so you separate the two atoms apart. Or you can also use the word ionize. Ionize means to form ions. Okay, so what happens is that when this covalent bond breaks, okay, the Cl atom is removed, right? Okay, then the electrons here actually goes to chlorine. So the bond broken hydrogen doesn't actually get back its own electron. It actually forms the H plus ion, and we have the Cl minus ion. That's why in the end they form ions. Okay, so this is your like H plus, Cl minus. Okay, so that's why we say acids, when you put them in water, they undergo this process of dissociation or ionization. So to represent in the form of an equation, HCl, AQ, because it's a solution, it dissociates, we show an arrow, to form the two ions respectively. Nitric acid, again, you remove your H plus, you get your nitrate ions back. Okay, sulfuric acid, you get two H plus ions because the formula is H2SO4 and one sulfate ion. Okay, one other acid is ethanoic acid, which is a weak acid. You notice that the symbol for the arrow here is actually a double-headed arrow. That means only some of these molecules undergo the dissociation process. Okay, so you get a lower concentration of your H plus ions. We will cover this later in another video of strength of acids. You probably learned in lower sec that acids react with metals, carbonates, or bases to form salts. Depending on the type of acid that we use, the type of salt form will also be different. So if you use hydrochloric acid, you get a chloride. If you use nitric acid, you get a nitrate, so on and so forth. I want to highlight that even though the formula of acids contain hydrogen, not all substances that contain hydrogen are acids. For example, methane CH4, even though the formula contains hydrogen, this hydrogen atom doesn't undergo dissociation. So you recall in the definition we said that acids only undergo dissociation in the presence of water. If the liquid that we add it to is not water, it doesn't undergo dissociation. For example, if we are using organic solvents. Organic solvents are carbon containing. That means this liquid is a carbon containing liquid. Example, we have tetrachloromethane, CCl4, okay, hexane, C6H14, so on and so forth. Okay, we'll encounter some of this in the chapter of organic chemistry, but for now, know that these are examples of solvents where acids do not undergo dissociation in. So if you look at a solution of an acid, we have your H plus ions and the other anion. Okay, so we learned in chemical bonding that your ions can move freely and become mobile charge carriers. This will allow an acid to be a good conductor of electricity. But if we want to talk about the properties of an acid or the reactions it undergoes, it is mainly due to the H plus ions. Why are acids corrosive is always due to the H plus ions. So take note when we use the term H plus ions or your free moving ions in general. Okay, so free moving ions we use when we talk about conducting electricity, and H plus ions we use when we talk about properties of acid, especially their chemical reactions. Okay, so there are two kinds of properties. First is the physical properties, and then we have the chemical properties. One of the properties of acids is that they have a sour taste, and that is because of the presence of H plus ions. Acids, they conduct electricity when they dissolve in water due to the presence of free-moving ions. And acids turn blue litmus paper red, and also due to the presence of H plus ions. You will find acids in many places in your everyday life. You may want to take a closer look at some of these substances and see what acids they actually contain. One example that you'll find very often is in Coca-Cola. Okay, so if you look at the label of Coca-Cola, you'll find that the acid it contains is actually phosphoric acid. And that's why some people say that Coca-Cola can be used to remove rust, can be used to clean your toilet bowl or remove stains quite easily because it has acids in them. So let's look at the first chemical reaction of acids, which is acid plus metal give salt plus hydrogen. I always remember this as always make someone happy. Acid reacts with metal to give salt plus hydrogen. So if our metal is zinc and our acid is hydrochloric acid, the salt will be zinc chloride. So the front part comes from the metal and the back part comes from the acid. So since we have already learned how to write chemical and ionic equations, maybe you want to pause the video now, have a go at it, then we'll go through the answers. Okay, so you should have something like this. Let me just go through with you again. So zinc forms Zn2 plus ion, and the chloride formula is Cl minus. When you combine together, you get ZnCl2. To balance the equation, we need to add a 2 in front here. So we learned before in ionic equation that you need to split the ions apart if it's AQ. So you have 2H plus, 2Cl minus. Zinc is a metal, solid, we don't do anything to it. Here we split back into the ions again, Zn2 plus 2Cl minus. And for hydrogen gas, we leave it alone. So you look at what is the same on the left and right hand side, cancel. Write down your final answer. So let's see what happens if you were to carry out this reaction in the lab. So after you add the piece of metal, you see effervescence. The metal starts to dissolve. When you insert a lighted spleen into the mouth of the test tube, the lighted spleen extinguishes with a pop sound. Take note, there are some metals which are what we call unreactive metals. So that means they do not react with acids, dilute acids in particular. And them being unreactive, right, is also the reason why they are used to make coins in the past. So copper, silver, and gold, right, you use a lot in jewelry making because they do not react very easily. But if you were to use concentrated acid, it is able to actually react with some of these metals. For students taking pure chemistry, we also understand this concept known as the insoluble coating, which we'll talk about quite a bit when we go to the chapter of salt preparation. So if we look at lead, right, when lead reacts with acid, again, you form a salt. This time is lead 2 chloride. But if you remember our solubility table, lead 2 chloride is an insoluble salt. Okay, so the salt here is actually a solid, and you get hydrogen. So what will happen is that because it's a solid, it will form this layer of solid around the starting material. And this gives it a coating, which is an insoluble coating, preventing the acid from coming into contact with the lead beneath it. So the reaction actually stops even before it is completed. Okay, so just take note of some of these exceptions to the general acid-metal kind of reaction. Another reaction is acid react with carbonates to form salt water and carbon dioxide. I like to remember this using always. Comfort someone who cries. Okay, I know it may sound a little bit cringy, but you can use your own acronyms to help you remember some of these reactions. I'd like you to give this a try first, pause the video, write the equations, then I'll go through the answers with you. Alright, take note that for magnesium carbonate, it is insoluble in water, so I put the solid state symbol. This one you can split to 2H plus and sulfate. Okay, this one you split to Mg2 plus and sulfate. Okay, the rest you don't actually need to split because they are solid, gas, and liquid. So only split the AQ, which means I only need to cancel this and this. Okay, so my final answer becomes. Alright, next, nitric acid and sodium hydrogen carbonate. The formula for sodium hydrogen carbonate is NaHCO3. Okay, so when writing the ionic equation, we split the AQ, H plus, NO3 minus, Na plus. Hydrogen carbonate has this formula. Okay, you can go and check our formula list again. Na plus, NO3 minus. Alright, let's cancel. This is the same on both sides. This is the same on both sides. Okay, so we have. So again, we will observe effervescence. To test for the gas, we bubble the gas into lime water, and a white precipitate is formed in lime water if carbon dioxide is present. How should the delivery tube be arranged when you test for carbon dioxide? Is it A, B, C, or D? A is wrong because the carbon dioxide can escape. B is wrong because nothing is being inserted into lime water. D is wrong because the reaction makes sure the carbon dioxide produced will escape. Okay, so take note, the long end of the delivery tube should always be inserted into the lime water. So this is how it's supposed to be done. There is another way we can test for carbon dioxide is by using a pipette, okay, to withdraw the carbon dioxide and then bubble it separately into a lime water without the use of a delivery tube. Let's take a look. This method involves us using the dropping pipette to withdraw a sample of carbon dioxide from the test tube or boiling tube and then bubble it into a separate test tube containing lime water. This method is useful if you're a bit slow in connecting the delivery tube, such that carbon dioxide, right, is quite dense, it tends to sink, so you have a little bit more time to actually withdraw the gas and then bubble into lime water manually without the use of the delivery tube. And the last reaction of acid will be acid-base gives salt water. So a base is any metal oxide or hydroxide. We can remember this as always become someone wonderful. So there are two examples here. Pause the video and give it a try. So remember, the metal comes from the base and the non-metal part of the salt comes from the acid. So if you use sodium hydroxide, your salt will be sodium something. If you use copper 2 oxide, your salt will be copper 2 something. Then hydrochloric acid becomes a chloride. sulfuric acid becomes a sulfate. Alright, check your answers. If you have any doubts, do come and approach me. The uses of acid is for info only, so if you're interested, go find out some of the uses of these acids. Let's take a look at this concept cartoon. Who do you agree with? Pause the video and think, and then we'll go through the answer. We have learned in the chapter of alloys that brass is a mixture of copper and zinc. You know that copper is unreactive, so it doesn't react with acids. Zinc is the one that will react. In a mixture, the different components, they retain their own properties. So the zinc reacts, zinc dissolves to form zinc chloride. The copper part is unchanged. Okay, so the copper metal actually is left behind as reddish brown solids. So you form zinc chloride, and zinc chloride is actually a colorless solution. So it's not that there is no visible reaction. It doesn't react completely as well. You shouldn't get a blue solution because the copper doesn't react. So student D is actually correct because the zinc reacts, leaving the reddish brown copper and the colorless solution of zinc chloride. I would like you all to consolidate your learning by completing this checkpoint page. Alright, let's go through the answers. This is a downward delivery method, which means that the gas is denser than air. It sinks. We have so far learned two gases that are produced from acid reaction. Hydrogen is actually less dense, it will rise. Carbon dioxide is actually denser, it will sink. So the gas here is actually carbon dioxide. The salt here is sodium nitrate. So acid plus carbonate give sodium nitrate plus water plus carbon dioxide. What acid do we need to use? Because the salt is a nitrate, the acid must be nitric acid. Because it's a sodium salt, we use sodium carbonate. Okay, so remember the front part of the name in the salt always comes from the metal, the base, or the carbonate. So how do you confirm the identity of carbon dioxide gas? If carbon dioxide is present, a white precipitate is formed in lime water. Okay, so next one, we see that lighted splint extinguished with a pop sound. This is hydrogen gas, which means that acid and metal reaction. We form zinc sulfate. The metal must be zinc. The acid must be sulfuric acid. So let me summarize today's lesson. Acids undergo three reactions: acid plus metal, acid carbonate, and acid and base. All three form a salt. The front part of the name of the salt comes from the metal, the base or the carbonate, and the back part of the salt comes from the acid. Okay, so sodium chloride, the front will be sodium carbonate, sodium hydroxide, or sodium metal. The back part depends on the type of acid that you use, and the products depend on whether it's an acid metal, carbonate, or acid base. So that's all for this video. I'll see you in class.